Hey tech enthusiasts, welcome back to Code Tech Chronicles. I'm Shashi Devendra and today we are diving deep into the topic that every programmer, beginner or pro absolutely must understand. Big O notations, the idea of time and space complexity. Let's begin with the fundamental question. Why should you care about time and space complexity? Well, imagine this. You are solving a problem and your code runs perfectly on a small test case. Awesome. But when you throw a real world data set at it, like thousands or millions of records, suddenly your program slows down and crashes or takes forever to respond. That's where complexity analysis comes in. Two developers might solve the same problem, but one solution could be 10 times faster than the other simply because it uses a better algorithm. Let me give you a simple example. Suppose you are searching for a name in a phone book. You could go through every name one by one. That's linear time, ON. Or you could use smarter strategy like binary search, which cuts the list in half at every step. That's logarithmic time or O log n. Same problem, very different performance. And this difference gets more extreme as your input grows. Going from 10 names to 10 million names, it's a totally different ball game, and only a scalable algorithm can handle it smoothly. So here's the real takeaway. Writing correct code is just a starting point. Writing efficient, scalable code is what makes you a greater developer. And understanding time and space complexity is how you get there. Okay, what is time complexity? Alright, let's get into the heart of the algorithm, time complexity. Time complexity is a way to describe how the runtime of an algorithm grows as the size of the input increases. It doesn't measure actual seconds or minutes. Instead, it gives us a general idea of how scalable our algorithm is. Think of it as a language we use to talk about speed, but in a way that applies to any machine, not just your laptop or mine. Now here's a basic example. Let's say you have a simple loop that goes through a list of n items, like checking each name in the guest list. That loop will take time proportional to n. So we say the time complexity is On, also known as linear time. Now imagine you have two loops, one inside other, both loops through the same list. For each time element in the outer loop, the inner loop also runs n times. That means the total number of operations is n times n or n square. So the time complexity is On square. This is called quadratic time, and it can get slow really fast as your input grows. For instance, if n is 10, On square mean about 100 operations. But if n is 1000, now you are doing 1 million operations. And that's huge performance hit. So understanding time complexity helps us choose smarter solutions. The goal is to avoid unnecessary work and keep your algorithm running efficiently, even when the data set grows from a handful of records to millions. And the best part, once you train yourself to recognize common patterns, loops, recursions, searches, sorts, you will start spotting time complexity without even thinking about it. Now that we have talked about how long your code takes to run, let's talk about how much memory it needs. That is what we call space complexity. Space complexity refers to the total amount of working storage an algorithm needs to complete its task. This includes all the variables, data structures, function call stacks, temporary storage, and even input data if you are duplicating it internally. Think of your computer's memory like a backpack. If your algorithm is light and only carries a pencil and a notebook, that's great. It's efficient. But if it's lunging around 10 laptops, a projector, and 5 textbooks, well, that's heavy algorithm. Your backpack's gonna flip up quick. That's high space complexity. For example, if your algorithm creates a new array of n elements, the space it uses grows directly with the input size. That's On space. Here's another case. If you just use a few variables like counters or flags, regardless of how big the input is, that's O1 space or constant space, but it doesn't stop there. What if you are using recursion? Each function call in recursion adds a frame to the call stack, and that eats up memory too. If you are making n recursive calls, your space complexity could be On, even if you are not storing anything extra. A lot of people focuses only on time, but in real world scenarios, space is just as important. Think mobile apps with limited RAM or embedded system where memory is measured in kilobytes. And in big data or machine learning, storing huge intermediate result unnecessarily can crash your program. So optimizing space isn't just academic, it's practical and crucial. So to sum it up, space complexity tells us how efficiently our algorithm uses memory, which becomes super important when working on memory constrained devices or large scale systems. By writing memory efficient code, we reduce the risk of crashes, speed up execution, and make our program more scalable. Now let's demystify a term you have probably seen everywhere: big O notation. Big O is a mathematical way of describe the upper limit of your algorithm's performance. In simple words, it tells you how well or poorly your algorithm scales as input size increases. Think of it as a speed limit sign for your code. Whether you are testing your program or on a slow computer or a supercomputer, Big O tells you what to expect when the input size doubles, triples, or hits a million. It ignores machine-specific details, constants, and less significant operations. Why? Because when you are processing big data or real-world inputs, those small details don't matter nearly as much as how your algorithm grows. If one algorithm runs in O(n) time and another in O(n) square, the second one will become significantly slower as the input grows, regardless of your processor speed. So, Big O helps us compare algorithms, make decisions, and write smarter, scalable solutions. Let's start with the fastest type of algorithm you can write, O1 or constant time. In the constant time, your algorithm executes in the same amount of time regardless of how big the input is. Whether you are checking one element or a million, operations takes a fixed number of steps. Accessing an element from an array by its index, like array fifth element, always takes one step. It doesn't matter if your array has 10 elements or 10,000. These are the gold standard, the most efficient operation you can write. While you can't always achieve O1, aiming for it is critical code section can dramatically improve performance. Now let's move into the most common type complexities, On and On square. On, the linear time. This means the time your code takes increases directly with the size of your input. If you loop through a list of n elements once, you are doing On work. For example, a simple for loop that prints every element in an array is a linear time. On square, quadratic time. This is where things get expensive. You are likely dealing with nested loops, a loop inside a loop. For every element in an outer loop, you're processing an entire input again in the inner loop. For example, think about bubble sort, where you compare every pair of elements in a list. That's On square operation. Why it matters? Quadratic time can quickly become bottleneck. With just 1,000 elements, you are making a million operations. That's why algorithm optimization is so important. Let's talk one of the most efficient and clever complexities, O log n, also known as logarithmic time. Imagine you are trying to find a name in a phone book. You wouldn't flip through every page. You might just go to the middle then decide whether to go left or right. That's how binary search works, cutting the problem in half at every step. For example, if you are searching through a sorted array with 1000 elements instead of 1000 steps, you only need about 10. Why it matters? Algorithms that reduces the problem size with each steps are incredibly powerful. They are the backbone of divide and conquer techniques. Here's a visual representation of how these time complexities scale. O1 stays flat no matter how big n gets. O log n grows slowly and steadily. On grows linearly, manageable for most cases. On log n grows faster but still efficient. On square and O2 to the power n, they explode. And that's why we avoid them whenever possible. This graph makes it super easy to see which algorithm scales well and which one doesn't. Let's break down some practical examples of space complexity. O1, constant space. An algorithm that only uses a few variables no matter how big the input is using constant space. For example, swapping two values in place like a, b is equals to b, a is O1. On, linear space. Here the memory needed grows with the input. For example, creating a copy of an array, storing results in new list or recursive functions with n calls all uses On space. A tip: watch out for the hidden space costs, like using recursion without considering the call stack. Okay, now that we have seen all the major time complexities, let's talk about how you can analyze the time and space complexity of an algorithm, even your own code. This is a critical skill that separates average programmer from top-tier developers. And guess what? It's not as hard as it seems once you know what to look for. Step 1. Count the loops. Start by looking at the number of loops in your code. A single for loop that iterates n times, that's On. A nested loop, where the inner loop also runs n times, that's On square. For example, consider the Python example. For I in range n and the inner loop for j in range n, it prints I and j. The outer loops On, the inner loops On, and the overlog On square. Nested loops are the most common source of quadratic and cubic time. So identify and minimize them whenever possible. Step 2. Identify recursion. If your function call itself, you have got recursion, and that usually means a recursive stack that grows in the background. Ask yourself, how many times does it recurse? Is it a tail recursive? Are you solving overlapping subproblems? Example, recursive Fibonacci is O2 to the power n, very inefficient. But with memoization, it becomes On. Is your algorithm breaking? Then we do step 3, spot, divide and conquer. And we can divide our problem into smaller parts like binary search or merge sort. Then you are likely dealing with O log n and O n log n. Tip: look for the patterns like this, where the function like divide calls over data, then it divides it in two parts, into subarrays, left and right, starting to mid and mid to end, and then again call divide on each of the subparts, left and right, and then merge the results. This is a classic divide and conquer structure. Step 4. Auxiliary space. Now look at memory. Ask, am I creating new arrays, list or hash maps? Am I copying data or modifying in place? Is my recursion depth increasing memory usage? For example, looking at the following Python code, we define a function double list, and in that we consider a new array with result for num in nums, and then it iterates over all the input elements and then appends in result the twice of each element. Here you are using on additional space to store the results. If you just modify the original list in place, that is the nums, space complexity could drop to O1. Step 5. Drop constants and lower order terms. When writing big O, always focus on the term that grows the fastest and ignore constants. Consider the following example, where there are two loops which prints ij. Even though you have two loops, the inner loop always run 5 times. That's constant. So the complexity is still on, not on times 5. Final tips for analyzing complexity. Look at growth. How does the algorithm behaves as input increases? Estimate in chunks. Break down the big functions and analyze each piece. Practice daily. Start analyzing complexity every time you solve a coding problem. So don't just write code that works, write code that works efficiently. Analyzing complexities make code faster, leaner, and ready for real world. And trust me, the more you do it, the more intuitive it becomes. Soon you will be spotting on log n in your sleep. Alright, here are the key takeaways from today's session on time and space complexity. Time and space complexity help you write scalable, optimized code. Big O notation expresses how performance grows as input grows. Focuses on worst case performance for consistency. Aim for algorithms that are time efficient and space conscious. Know the common complexities. Use this knowledge to choose the right algorithm and refactor poor performing ones. Thank you so much for watching this episode of Code Tech Chronicles. If you found this helpful, go ahead and like, share and subscribe. And don't forget to tap the bell icon so you never miss a video. Most importantly, remember, small steps, big impact. Keep learning, keep building, and I'll see you in the next one.